Thanks everybody, I'm Nicola Assolini. I will present you joint work with my supervisor in modeling the denotational semantic of quantum loop. So in this work we are considering quantum loops, so we are basically modeling something that has to deal with the control flow in quantum program languages. So like in quantum program languages we can use different kind of control flow. There is the most basic one that is a classical control flow, like for example in Qiskit, in which you have a classical program that builds a circuit basically. You can do it the control flow more quantum, including like the measurement in the control flow. In this way you are more expressive, but your control flow is still probabilistic, but it's related to the quantum state. Then you can go further in this, introducing some quantum if statement that can help you in writing some algorithm in a more high-level way. And starting from this kind of if statement, you can have like some more exotic stuff, like a while loop or a recursion that is based on this quantum if statement. And here is where we want to work. In particular, we are considering a loop in which the guard variable is quantum. That is the equivalent of a recursion. Of course, a while loop is a pretty basic statement in classical computing. In quantum, it's bringing some problems. First of all, when we have a quantum loop, usually we expect to change the value of the guard inside the body of the loop. Because if not, we are simply doing a for loop or a loop that will not terminate. And this, of course, is a problem in quantum because, as you know, you cannot build something like this one with quantum computing because it will be not reversible, not unitary, it will be against the cloning theorem. So the first things to solve is find a way to represent in a unitary wave a self-control operation. You can do it in different way. What we have used is using a temporary variable, that is the first wires, and then if you want to implement something like this, we perform a quantum copy and then perform the body of the self-controlled operation using this temporary variable. Of course, this is not exactly the same of a self-controlled operation, but since the operation itself is not reversible, we need to do some change if we want to implement it. Then, starting with this, we can try to build a circuit that represents this quantum loop. So, this circuit will need a list of temporary variables, a lot of temporary variables, and then we can start building these two gates that correspond to the first iteration, then the second one, and then go on till some k that will fix according to how much temporary variable we have in our circuit. So now that we have a circuit description, we can try to model it mathematically. So here we have our instruction. We can compile with this kind of circuit, going deep in this recursion as much as we want, also we can. And mathematically, we can describe this circuit using our recursive equation. So we can start with the base case, that is like a W0, that means no loop, so the identity, we are not doing anything. And then we can have this other case in which we are describing the quantum loop. In particular, we have the first piece, that is the C0, that corresponds to the first instruction, so we are doing the quantum copy to the temporary variable. And then we have the second part that corresponds to these two operations. So we are saying this is just another way using projector to write the control operation. So if the temporary variable is 1, perform this operation, so the body of the loop, and the rest of the iteration. If not, do nothing. Here I'm considering a simple loop with only one variable, but of course we can have more variable here, simply the U operation will be bigger. We can see how this work with a simple example. This is again a while loop with only one variable that basically only do Hadamard. So it does not compute anything, but it's a nice example. We can see how this works starting from this state in which we have all the temporary variable to 0, and then Q that is in uniform superposition. So this is the equation. It's as before. Here we have put Hadamard because it's the body of the loop. And then we will have the first case is the identity, so we do nothing. We simply return the initial state. Then there is the operator that model only one iteration that corresponds to doing this circuit. So when Q is 0, we do nothing. When Q is 1, we negate the temporary variable and we apply Hadamard. Then we can go on, for example, with W2, that model up to 2 iterations. So it's like applying W to this one. So here we see that we may have done 0, 1, or 2 iteration, because in this case it was already out of the loop, so we do nothing. In this case, it depends. If Q is 0, we exit on the loop. If Q is 1, we apply Hadamard again. Like in general, this will be like the general equation, so we are like collecting all the termination part, and then we like a second part that they say that it becomes smaller, smaller, and smaller. And okay, so here we have described with that equation basically this circuit bounded to some k, because of course if we want to implement this in a circuit, since the circuit is finite, we need to fix some maximum possible iteration, do all the rolling, and we will have a circuit that model the loop up to some k, some maximum iteration. But like in general, since we want to describe the semantic of this operation, we are interested to model this operation for every n. So we're interested like to see what happens if we take this one and we go basically to the limit of a that go to infinity, like to see what happens to a while loop, like for any possible iteration. With the unitary operator, we cannot actually do that because there is this theorem that basically creates a sufficient and necessary condition for a sequence of linear bounded operator to have a limit. Of course, we are unitary now, so we are a special case of bounded linear operator. In particular, to have a limit, this sequence requires to be if we consider the sequence of the norm, this sequence must be bounded. In this case, we are fine. We are all unitary, so the norm is always 1. But there is also this second condition that say that it must exist a subspace of our Hilbert space such that every element in this space, for every element in this space, the sequence of our operator applied to that x must be a Cauchy sequence. And in our case, we violated this equation. I can give you an idea why this happened. We can consider again our example. As before, we can visualize it how we can see how it acts on the state using a visual example. Here I have represented the evolution of the state of Q, forgetting about all the t for being shorter. So if you have like this semantic, we will have like the base case that does nothing, so return the original state. We will have the first iteration that apply only one CNOT and one control Hadamard that basically return this state. We will have the second iteration that return this state because we did only one iteration, and then we may have done 2 iterations, so superposition between this one and this one. The third iteration will be there, and so on. Now, if you see, this is pretty odd when you usually define a denotational semantics. In fact, like if we look to the standard classical denotational semantic of our loop like this one, usually you start from the void state or the bottom state. So usually your base case is like the program that does nothing. And then you collect all the possible termination for this program for all n, and then you take the union for all possible n, and you get the semantic of the loop that basically contain everything that can terminate. Here it's not the same things because the base case is already, okay, it's the identity that means do nothing, but it's not like a function that does not compute nothing. It's the identity. And then at every step, we are actually collecting something because, of course, we are in quantum, so we may have superposition between execution. So starting from a state is like we have more than one possible execution, basically. So we are collecting something, but at the same time, there is always a piece of the state that is different for each operator. And this happens because we are unitary. So if we take a state that is normalized, we must return a state that is normalized. So we cannot just return this. We must return also the last part, the older part of the state, because I don't know, if we want to return only the terminated part of the state, this will be not have norm 1. But this fact that we are always keeping like this part of the computation that we can call like the going on substate, so the state that contain what is not completely computed yet, it's what basically make the sequence of our operator applied to a fixed vector not Cauchy in general. So we cannot have a limit, and in particular we cannot have a limit because we are unitary, basically, because we need also to have this part of the state. So, but we want to modeling like the notation in a more general way and can be useful to understand how this loop behave for every possible n. So what we can do is, starting from this, we can decide, okay, we don't want to be necessarily unitary. We can just be a linear bounded operator. And we can achieve this by simply changing the base case. If here we choose to do this, so we take as a base case the null operator, and we keep the same recursive equation, what happens is this one, that if you consider again our example, but this time we consider the linear semantics, we will have like the base case that is the null vector. So it's basically it's like an empty set. Then the first case, we return only what is terminated, because if we briefly come back here, if this is 0, after the first iteration, this is 0. So what return L1 is apply the C0, project on 0. So like apply the C0 and return only when the state, the guard is false. So here we will have only when the guard is false. Then we will have L2. Again, we start from this one, the guard is false, this is remain, and we add the second part of the state when the guard is false. And so on. So what we are doing here is like collecting the top part of the execution, but not the bottom. So we are collecting only the terminated part of the state, not the going on part of the state. And with this change, we're able to, again, according to this theorem, we are fulfilled, of course, this condition because we are linear bounded, but also this other condition, because this time, if we're considering that equation, this sequence, it will be a Cauchy sequence for every starting vector. Thus, we have a limit. So we can say that like the denotational semantic of our quantum loop is the limit of this sequence. And moreover, you can also like give a more characterization of this limit. In fact, since we know that this sequence is only Cauchy, we always have a limit, so we can like say this limit will be the linear operator that map every standard base, or in general every vector, in this limit, because we know that this limit exists. So, what we have introduced here, we are starting from a quantum while loop, and we have defined two semantics with two different meanings. We have the unitary semantics that can be seen like a circuit representation of the while loop, so can be seen as sort of like very naive and unoptimized compilation that allows us to represent exactly the behavior of the while loop, or one of the possible behavior, because you can always choose a different way to make the self-control operation unitary. But like after you have fixed that way, you can build the unitary semantics, and you will have like a unitary semantics that describe you how a possible quantum loop behave on a quantum computer. Of course, up to some k, because like there are a lot of work about this, but basically we cannot like leave this while loop run, because like there's no way to understand when a quantum Turing machine alt from outside, so we always have to fix some k, and then like I don't know, we want to do 1,000 iteration, we will have the unitary description, this 1,000 iteration. But at the same time, if you are interested to modeling this quantum loop more generally, we have the linear semantics that allow us to define a limit of this loop. So we're able to describe the behavior of the loop for every n. And in particular, the way in which two semantics are related is the following, again on the same example, because what we have here, we have like the linear semantic that collect everything that is alted, basically, every part of the superposition of execution that is alting. And then we have the unitary semantic that has something more. So from here, from this slide, we can see that like we can consider the linear semantics like a sort of under approximation of the unitary semantics that does not have a limit. It has a lot of problem of being unitary. So we can like under approximate the linear semantics, discarding a piece of information. These allow us to have a general description for every n. And moreover, if there is a loop that alt for some input, basically at some point this part will be empty, because also the unitary semantic, if the loop half at some point will contain only a determinative state. So like when a loop is halting, is a loop that halt, we are sure that the linear and the unitary will be the same. If the loop may not halt for a certain input, or may halt and not halt in superposition like this one, here we have a very small state that does not halt, but there is always a piece of one possible one of the superposition of execution that can go infinity. We have the linear that basically model everything that is computed by the loop. That compare the unitary. So like with the linear, we are able to study what actually the loop is computing, even if the loop is not completely halting in the quantum domain. I think that I can conclude since it's almost lunch break. So thank you for the attention. That was the work. If you're more interested here, like on the website, there is a draft of the paper that we will upload on archive soon, I hope. And one more thing, I'm almost finishing my PhD, so I will be on the job market soon. So if you are, okay, this is part of my research, of course. I also work on static analysis and data interpretation for quantum computing in general. So if you think that if you are hiring or your company or your university is hiring and you think that my competence can be useful, I will be there for the whole week, so please talk to me. Thank you.
Very good. Thank you very much, Nicola. So now for some question. Is there a question? Yep.
Thanks, Nicola. Obvious question, why not recycle the ancillas instead of having an infinite pool of them?
Okay, so the point is, there is like a result, I don't remember the paper, in which like in general when you have something like this, I think that it's like control machine of the title, quantum control machine, something similar. When you have like something like, you have to find the circuit. Like in general, if you have something like this one, you cannot define like a general algorithm to do the computation of the ancilla, because there is like a sort of circular dependence between the value. So like in general, you cannot use it. So you need, like if you want the general definition, you need the infinite ancilla. But like, I mean, if you are probably, since everything is irreversible, we are in quantum, so like if you're, I don't know, building the loop for a specific algorithm, so you know how the state will be at the end, I think that you can do it. I mean, it's better to do it, of course. Also because what happened here is that you have created an entanglement relation. It's not necessarily good. So yes, in general you can't, so this is why we didn't include in the definition of the semantics, but like for specific case you can, of course.
Yeah, thanks for the talk also from my side. Mine is not that much a question, but rather a comment.
Okay.
There's also another type of quantum loop that could be considered. It is coming out of this paper called the quantum control machine.
Yes, okay.
And within this model of a quantum computer is like actually like maybe like one level above the circuit level. Because the quantum control machine, it kind of loads its program in superposition, and it also has like a pointer that like moves through the program,
yes,
and the pointer can also be in superposition. And within this model, you can also have loops like that. I'm not sure if it can have arbitrary unbounded loops, but a key insight here is that the quantum control machine also like always operates in cycles. So it like loads instructions, it executes the instructions, and then it unloads the instructions.
Yes.
So that might be also like an interesting direction to go.
Yeah, I think that like can be. I think maybe this can be like a more. I think that they have in mind that what you're referring. Probably, I'm not sure. We can talk later, but like I think that is more like a generic. I mean, you can always translate the quantum, like the quantum machine in a sort of circuit representation with the pointer will be other variable. So like this should be like a more. I mean, I think that you can model that work in this semantics probably. I mean, if you want, possible model loop, of course.
Okay, no more questions? Oh, yeah.
Yeah, just a high-level question. So,
Yes.
do you know why you can use
Yeah, okay.
quantum loops?
This is a good question. I mean, there is not like a known, I think, like known or used algorithm that exploit these kind of things. I mean, I don't know. I mean, okay, I can imagine why, because it's not easy to like actually having this kind of feature. I don't know if there is like this sort of why quantum recursion of quantum are not used because there are not like simple way to implement it. So like basically nobody think to use it, or because it's difficult to also like to think in this way, maybe because with superposition between execution, or it's not useful in general. So I don't know. I mean, I was like an example, I think, in my extra slide. Give me 1 second. No. What is this one? Okay, I was thinking like an example here, for example. The only thing that I may think that this can be useful, like for what is now, is like for like implementing like quantum walks with some condition. This is like what I like to call like a gambling quantum walk, because basically like a quantum walk, you have the coin, the value, but you can go on till the value is positive. So like a gambling, if you finish the money, you're out of the game. So like if you want to implement some like they want to model that can go only in basically one direction or with some boundary, you will need something like that, or like probably visit graph or some kind of stuff. But like yes, in general there is not like some like famous algorithm. Okay.
Thank you very much one more time, Nicola.